Good morning. I'm Nick Watson from the University of Nottingham, and I lead the Sensors Special Interest Group as part of UCAN Plus with Rob Joyce and Jenny Grisatova from the University of Sheffield. And in this short video, I'm just going to talk about some of the scientific areas and industry challenges that are emerging as part of the Sensors Special Interest Group. And this information just hasn't come from myself, Rob, and Jenny. It's actually, we went out to the members of the SIG and surveyed them and asked them to provide some input that we've summarised on these slides. So what we've tried to do, excuse me, is group these into areas, and I'll go through these. But you will say there's some areas of repetition, which I think are really important. So within the scientific areas, we've got emerging technologies. And within there's areas such as swarm sensors, so more than one acoustic ultrasonic sensor, high power embedded sensors, so how can we put sensors in components, distributed fibre optic sensing, high temperature and flexible sensing. So this is all of our new technologies and making new ultrasonic acoustic measurements in different ways in different places. Second area is turning data into information. A lot of the work in acoustic and ultrasound measurements has been on the physical understanding of the wave propagation. In the last few years, we've seen a rise of more use of statistical methods, AI, machine learning, and I think the whole challenge here is about how can we take a measurement and turn it into information about a system, about a space, about a material. I think one of the areas I can see a lot of growth being in is hybrid models, where we have then with each combine the data-driven statistical methods and the first principle models. On the AI and the machine learning side, I think there's going to be lots there, but I think it'll be more around the there's more of a need around interpretability, explainability in those models, and especially if they're going to be adopted by industry. Methods that translate from one situation to another. Again, this links a bit into the machine learning side, so look for areas around transfer learning, domain adaptation, and obtaining reliable, accurate and useful results under operating conditions and environments. So we've done a lot of good work in the lab, but how can we develop sensors that work really effectively, work reliably in challenging environments, the real world? And then the final bit is multi-sensor data fusion. That can be combined data from different acoustic sensors, or it could be acoustic sensors with other types of sensing, so optical, for example. The third scientific area is enhanced sensor capability. So this is looking at behaviour, use, informed design, so different types of metamaterials, passive materials, and connecting the function of the physical transducer with the signal process in the actual application. So thinking about how this sensor is going to be used, and using that information to really design it and make sure we've got the best pipeline through those different stages. I think at the minute what tends to happen is there's a new application and you'd look at the literature, or you'd work back to see what other people have used and just use that. We're actually looking at this a bit broader. Something we spoke about earlier, which is the integration of sensors with electronics. It's got intelligent sensors, so there's lots around edge computing, AI on the edge, things like this are really big, so can we get the sensors there as well? And use of sensors in sets, networks and swarms. The final bit again is active feedback to change the sensor sensing parameters. So can it learn to make better measurements or measurements that give you more information? Going to our industry challenges, these were the first group was physical improvement to sensors, so reduction in size, power, ones that can work in production environments, so robust, tolerant, work first time, every time, 3D directionality, and other things around sensitivity, bandwidth and dynamic range, and the reliability of the data they produce. Second one is quite specific, but an area where we think there's a big opportunity for acoustics, and that's aggressive environments. So this could be challenging production environments, this could be deep under the ground, this could be in the sea, or this could be on other planets, for example. So we could look at high temperature, 200 degrees plus, and things like that. And the final part of this is very much linked in the industry challenges around Industry 4, so fourth industrial revolution, and this is having sensors embedded into components. So we already see a lot in manufacturing vibration, for example, assessment for machine condition monitoring, but there's lots of other opportunities there. So in my area, kind of more the food and drink process manufacturing, we can use it to look at things like online rheology, flows, leaks, things like that. but also things like processes that are used in other manufacturing sectors, so machining, welding, and in situ gauging of performance of components and processes. So that's just a super quick overview of some of the scientific areas and industry challenges. And I guess when you're putting together these proposals, I'd really encourage you to look at the interdisciplinary aspects. So what kind of areas can you address with skills from different disciplines, and then do some great research.